Hubble stares deep, Webb stares deeper. Roman will stare wide. And that single difference will reveal things about the universe that neither of the other two telescopes can physically show you. The Nancy Grace Roman Space Telescope is not an upgrade to Hubble or Webb. It is a fundamentally different instrument built to answer questions that require seeing enormous amounts of sky at once, rather than zooming in on a single point. And when it launches, currently targeted for no earlier than late 2026, it will produce the most comprehensive map of the infrared universe ever attempted from space. Start with the field of view. Hubble's primary camera, the Advanced Camera for Surveys, captures a field of view of roughly 3.4 by 3.4 arc-minutes. Webb's NIR-CAM captures about 2.2 by 4.4 arc-minutes. Roman's wide-field instrument captures 0.28 square degrees, roughly 100 times the area of Hubble's camera, in a single exposure, at similar resolution. What that means in practical terms, a single Roman image covers the same area of sky that would require approximately 100 Hubble pointings to map. Each of those Hubble pointings would take hours of observing time. Roman has a 2.4-meter primary mirror, the same diameter as Hubble's, but its optical design is optimized for a wide field rather than deep zooming. It achieves Hubble-like resolution across all 18 detectors simultaneously, covering that 0.28-degree field at a pixel scale of 0.11 arcseconds. The result is an instrument that combines the sharpness of Hubble with the panoramic coverage of a survey telescope. The science this enables falls into four major categories. First, dark energy and dark matter mapping. Roman will conduct the high-latitude wide-area survey, imaging billions of galaxies across a large portion of the sky in multiple wavelengths. By measuring the shapes of those galaxies with extreme precision, scientists can detect the distortion caused by gravitational lensing from intervening dark matter, a technique called weak gravitational lensing. Mapping this across billions of galaxies simultaneously will constrain the distribution of dark matter and measure how dark energy has affected cosmic structure growth over billions of years with precision that no previous survey has achieved. Second, exoplanet discovery. Roman will conduct a microlensing survey of the galactic bulge, the densely packed central region of the Milky Way, searching for planets by detecting the brief brightening of background stars when an intervening planet's gravity acts as a natural lens. This technique is sensitive to planets at orbital distances similar to Earth's and beyond, complementing Kepler and TESS, which were more sensitive to close-in planets. NASA estimates Roman could discover tens of thousands of exoplanets this way, including Earth-mass worlds at Earth-like orbital distances. Third, Type 1a supernovae surveys. Roman will detect thousands of supernovae across cosmic time, measuring their distances and brightnesses with a statistical power that allows a new level of precision in measuring the universe's expansion history. These measurements directly probe dark energy, its strength, whether it changes over time, and whether the cosmological constant is truly constant. The Hubble tension, the current disagreement between measurements of the universe's expansion rate, may either be resolved or deepened by Roman's data. Fourth, Roman carries a coronagraph instrument, a technology demonstrator designed to directly image planets around nearby stars by blocking the host star's light. This will not be the primary science driver, but will test coronagraph technology at a level of contrast improvement over 1,000 times better than Hubble's coronagraph, directly informing the design of future missions aimed at imaging Earth-like planets. Roman is named after Nancy Grace Roman, NASA's first chief of astronomy, who was instrumental in making Hubble a reality. The telescope's program cost is approximately $3.93 billion as of recent NASA budget documentation. What Roman represents is the strategic completion of a triangle: Webb for deep infrared imaging, Hubble for ultraviolet and visible precision, and Roman for the wide-field infrared view that maps the statistical universe. No single telescope can do everything. Roman does what neither Webb nor Hubble was designed for. The universe at scale, its large structure, its dark components, its full population of worlds, requires a wide eye. Roman is that eye. Follow for more on the telescopes that are rewriting astronomy. And tell me, If Roman can map billions of galaxies and find tens of thousands of exoplanets simultaneously, which discovery do you think will matter more? What dark energy actually is, or how many Earth-sized worlds are out there?